The finite element method had a big part to play for me when I learned about it in the 1970s. Engineers were creating it full time. It was just wonderful.
Welcome to a new episode of the Engineered Mind podcast. I'm your host Yusuf, and on this podcast I'm talking to researchers, scientists and engineers and how their work is shaping the world around us. For this episode, I'm very honored to welcome Gilbert Strang to my show. Gilbert has made many contributions to mathematics education, including publishing 7 mathematics textbooks and 1 monograph. Strang is the MathWorks Professor of Mathematics at the Massachusetts Institute of Technology. He teaches Introduction to Linear Algebra and Computational Science and Engineering, and his lectures are freely available through MIT OpenCourseWare. Professor Strang is well known for his unique presentation style that many find to be both entertaining and highly informative. In this podcast, Gilbert and I talk about Gilbert's principle of teach and don't grade, free versus paid education. Gilbert gives us anecdotes about the finite element method and his misconceptions when he worked on FEA. We talk about deep learning, the mathematics behind it, and what motivated Gilbert Strang to write about AI and big data. Gilbert will also talk about the aspect of coding versus theoretical math knowledge. We discuss open problems in mathematics, the programming language Julia, his favorite matrix, and so much more. And now, ladies and gentlemen, here's my podcast with the one and only Gilbert Strang. Today we have an absolute legend on the podcast, Gilbert Strang. Thank you so much for attending and coming to my show, actually.
Sure, it's a pleasure.
Yeah, you're kind of a math rock star or math legend, as some people would say, and you have educated millions and millions of people over the years. Usually we let people who are guests on the podcast introduce themselves, in 1 or 2 minutes, to keep traditions alive. Could you maybe introduce yourself, Gilbert, to the few people who don't know you?
Oh, that's fine. Sure, I'd be happy to. So I'm Gilbert Strang, or my friends sometimes call me Gil. And I was a student at MIT, and then in Oxford, and then in California, and then back to MIT for a teaching appointment. And I have stayed there ever since. So that's about 60 years, I'm sorry to say. So I've taught linear algebra especially, and finite elements. Finite elements was a wonderful adventure. I would like to tell you about how that changed my life. But just jumping ahead, then came textbooks and videos on linear algebra, which has become my subject, and that's the big course I created at MIT. And now the new course is linear algebra and learning from data, with a little bit of AI and deep learning included. So that's my life. The possibility of doing those video lectures for 1806 linear algebra just came about the year 2000, and the cameraman just went into my class and took a picture as it ran, and no changes, no edits, and I'm very, very happy that the people have approved of it, enjoyed it. Yeah.
Excellent. I love it so much. And Gilbert, I have to ask you about your teaching method, because there's one quote from you saying, you are here to teach and not to grade. Yeah. I love that quote so much.
You heard that. Yes,
yeah, I've heard that, because when I was in university studying mechanical engineering, usually a lot of professors they like themselves by giving grades to people who are not that good. But you take another approach, you rather teach people than to grade them. What is the approach, or what is the idea behind that?
Well, it's my natural instinct that I love to see people understand something that they didn't really have straight before. And so at the end of the semester, I have to give grades. It's part of the job, but it's not the part I like, and it's not the part I pay a lot of attention to. So I keep telling the students, just let's be together and learn. Some of them probably are doubtful. They think, okay, this professor is still grading me, but really, it's well, one gives a lot of A's to tell the truth, and I think the important thing is learning. I mean, that's really the purpose of the university. It's why why I'm there, and it's why the students are there.
Mm-hmm.
Yeah.
Yeah, that makes a lot of sense. And also about your teaching methodology, I would say, is that sometimes when you solve a problem, then you go through the problem in your own head and you talk while solving the problem, which gives students insight to your thought process. Is it something you do subconsciously, or do you do it on purpose to also give students the idea of there's not only one way to solve a problem?
It really is subconscious. I just do it and think about the problem as I'm presenting it in the class or on the video. It's becoming kind of just the natural thing for me to think about the problem together with the students, together with the audience, and you know, new ideas come, so some extra comments are there. Yeah, it's learning. That's what this is all about.
Mm-hmm.
Yeah.
When it comes to the topic of free education, of course, there's this MIT OpenCourseWare, where every video from you is published freely accessible on the internet. How do you see the difference between education that's freely publicly accessible, like your linear algebra classes, and like lectures you have to pay for? Where do you see the big difference? Do you think at some point it might make sense? Where do you see the threshold?
Well, that's absolutely right. That that MIT took this decision. It wasn't there. They didn't expect to make the decision to be free. The expectation was that the lectures by faculty would somehow be sold or there'd be payments. But it's just so much better without that, and it's really it's become a nice thing so that people feel MIT is like friendly, which it is, and not this castle of professors who are just talking to themselves. That's no use. And let me say that the finite element method had a big part to play for me. When I learned about it in the 1970s, engineers were creating it full time. It was just wonderful. So among the things that I learned from finite elements was, well, I learned about some important problems that people really wanted to solve. And I learned about this good method, finite elements, for solving them. And then at some point, it was natural to write a book about the math side of it, the understanding from the point of view of functions and spaces of functions. So that was the first book, and I learned a lot about myself in that book. I enjoyed writing it. I remember now where I went, where I sat down to do most of the writing. And so anyway, after that book, then came a book on linear algebra, and my whole life was changed. Yeah. So finite elements is like a happy memory.
Yeah, it's good that you mentioned this. We wanted to talk about it at the later part of the podcast, but it's good that you mentioned the finite element method, because I wanted to ask you about linear algebra specifically, because it has so many applications. Whether we talk about deep learning, big data, finite element method, computational fluid dynamics, like it's everywhere. Yeah. And I know that from one of your interviews when you wrote the finite element book, you had some misconceptions about the finite element method, and actually Zinkowitz, who is like one of the pioneers in the finite element books.
Yes, he was.
He published, like, in your own words, like the really good fundamentals on FEM. What would you say, like, in your finite element book, what were some misconceptions that you had about FEM?
Well, let's see. At the very beginning, I was doing it in I was working in the special case of regular meshes, where all the mesh elements are squares or cubes, and in that case, and then the whole region was a square or a cube or a rectangle, maybe. So that was a first book that never got published, because after I wrote it, I learned really that the whole point of finite elements was the flexibility in the geometry. You didn't have to work have the domain be a square. You could take any domain and divide it into triangles or quads. So that first manuscript never saw the light of day, and I started over again with what I think is the real thing, with the flexibility in the geometry. Yeah, so that all came from talking to Oleg Zinkovich. Certainly, I remember actually driving in deepest Germany with him on a venture at a workshop, I guess. Yeah, some remarkable people helped to create that.
Yeah, you've got memories attached to the FEM and also the book that you've written then. But it's also still available, right? The FEM book from you?
Oh yes, it is. It is, and I did a new edition with an additional chapter or two on more recent developments. Mm-hmm. Yeah, and then other people have written more extensive math books that present what the mathematician sees as the key points. But of course all the engineering books that have come. Yeah. Mm-hmm. Is Oleg's book still a major source of a reference, or is that day gone?
You mean the Sinkowitz book?
Yeah, the Sinkowitz book.
Yeah, it's often cited in the finite element lectures, like in.
Yeah, I see. Right. Yeah. He was a great man. Yeah.
So interesting. Before we jump to the topic of deep learning, and also what would you say are the biggest, maybe 3 misconceptions or big misconceptions people have about linear algebra in general?
Well, let's see. First of all, a lot of math professors don't realize that linear algebra has become so important. They tend to, in some places, that message hasn't got through. Calculus is still everything, and so the students do 3 semesters, and then they do differential equations, and then maybe somewhere along the line they learn to multiply 2 matrices. Well, they don't even do that right, because I think of matrix multiplication as more than just a whole lot of dot products. The dot product picture is not doesn't show you vectors. That's the point. Those columns and the rows are vectors, and you're taking combinations. So that's another story, probably. So so the mathematics of and faculty don't realize that linear algebra has become so important. Deep learning tends to be within computer science and electrical engineering, and not so much in math departments. So that's why I introduced a course in our math department, and students come from all over MIT for that. Yeah.
Yeah. I mean, I would have not assumed that you, Gilbert, would write a book on big data / deep learning. I mean, obviously it might make sense, right? You teach linear algebra, so you might also write a book about deep learning or like machine learning. But what fascinates you about deep learning, and what was the initial idea, the thought process to write a book? Because there's a plethora of books out there. What was your idea to write a book like this?
Yeah. Well, first of all, like finite elements, anybody could see that this is a method that's working, and it's here to stay, and it's solving big new problems. So just the way finite elements are done. So I'm thinking, okay, how to get a picture of the whole picture of it's creating a function. I call it a learning function from all the layers of the network and the construction of the weights. It's creating some function that matches the training data. You could say, if I use a math word, it tries to interpolate the training data. If you know maybe 1,000 training cases or 10,000, you try to find a function that gets those correct, identifies those correctly, and then you hope that it will give a good answer for new data, test data that you haven't seen. Well, that's the problem. And of course, there have been many ways to fit a function to the data. Interpolation is taught in just, fitting a polynomial through points is a classical method, and everybody knows it's not very successful or stable when you have a lot of points. But here, this new method is successful. So that's the challenge for me, is why is this new method succeeding where older methods simply failed? We had no good way to fit a lot of data, and now we do. Now deep learning, that piecewise linear, typically using a ReLU nonlinearity in the middle of the neural net, has just answered a question that we did not have an answer to previously.
Mm-hmm. I see. And also in your book, which is, I think, very beautiful, as you start from the fundamentals. So everything that deep learning builds on is basically things like stochastic gradient descent, for example.
Sure.
And then you have all the topics in your book and building your way up in terms of increasing difficulty.
Yeah. All the topics except coding. That's not my world. So I don't, and other people do it, of course, very well. And there are lots. A beginner can get a lot of help from Keras or all the tools. So my part, like finite elements, my part is just to try to understand what's happening at the function level, so to speak. Yeah, that you're creating this function out of. You remember the function involves L different layers. Each layer, you multiply the previous layer by a matrix, and you add a bias vector, and then you do the nonlinearity, the ReLU, and then do it again and again. Very remarkable functions are created very quickly by that composition. Can I use the word composition? A function of a function of a function. Mm-hmm. It's sort of the. And that's what, when you want the derivatives, you need the chain rule. If you have a function of f of g of x, the chain rule is, df dg, dg dx. So, and that's what back substitution and the processes, the computing processes produce. Yeah.
Mm-hmm. I see. So before we jump, because you mentioned Keras, I want to ask you a question about software. But before we jump into that, I see that you're very curious, Gilbert. Like your whole life, you have been very curious. Like when you see FEM or like deep learning, you want to know the fundamentals. Do you think that something students are lacking, maybe, especially nowadays in a fast-changing world, that they need to be curious to understand complex problems, but they cannot really grasp the basic concepts? That's where they are saying math is hard, for example. Do you think that's the case?
Yeah, well, I mean, everybody does what's natural. I couldn't code anything. I mean, I'm just like, that's a different world. And other people would say, oh, sure, just code it up. Well, that would take me another lifetime. So everybody does what's sort of natural. And in this area, experiments and trying new ideas has been the way to develop. I guess the same was true maybe for finite elements. People were inventing new elements and then kind of had a structure to put them all in. Similarly with deep learning, of course, the big invention of using convolutional nets, convolutional matrices. So those matrices are the sort of so much easier, so many fewer parameters, and so it's just sort of natural choices that had to happen, that convolutional nets would be valuable. But but so many other great ideas have come, and I'm just impressed by them all.
Mm-hmm. When we talk about software now, because you also mentioned coding, do you think it highly depends on the teacher? Because I think you have a lecture with Mr. Moeller by combining solving partial or ordinary differential equations by using MATLAB. Do you think there should be a right mix of coding it up and knowing the theory, or do you think how do you think it should be distributed, like 80-20, 50-50?
Well, I do think a person should try to know both. Try to know how to code it, make it happen, and try to understand, whoa, what's happening at some level. But as I say, everybody fits in. So Cleve Moeller, of course, who was the creator of MATLAB, it was natural and the ODE suite within MATLAB. So for the differential equations book, he's my friend and a good expositor of MATLAB's suite. Then for deep learning, there are a lot of good books about how to code. Maybe my answer is again, just do what you can. Learn about the rest. Yeah, my contribution would never be something about coding, but I am trying to. I didn't feel that I had a full understanding of backpropagation. Why is it so successful? Well, there's simple ideas there, but I needed to get them clear, and so now I'm writing a paper with one of my students because it came from his project that explained just the simple idea of why go backwards in the backpropagation algorithm, why compute derivatives from the output instead of from the input. Yeah, it's simple when you see it.
I think so, and also once the paper is published, I can put it in the description of the podcast so people can have access the paper and read about it.
That would be fine.
Yeah, so keep me posted, and I'll put it in the description, Gilbert. I'm happy to do so.
Okay, it's not complete yet. It's halfway. Okay. Or more. I'll say more than halfway. So yeah, we'll be happy to do. I'll send that to you. Yeah, okay. It won't be long because the idea is just the point is to try to express in just a few pages why backward is the natural way to do the chain rule in computing. Yeah.
Excellent. Yeah. Of course. Cool. Gilbert, I would like to ask you, do you know about open problems in mathematics that you personally try to understand, but maybe they're super hard to grasp for you, even for someone like Gilbert Strang?
There are many deeper mathematicians. Who live their lives in going deeper and deeper into a part of some part of mathematics or connecting different parts. So my role is more to get an understanding of how the application can be sort of organized and then to write about it. So I got involved with wavelets after finite elements. I don't know if wavelets, does that mean anything? It was an exciting time. I don't think I'm sure it's not going to live and grow in the same way that finite elements. I mean, it's amazing with finite elements that new methods are still developing and new applications. Yeah, so wavelets are another rather remarkable functions that had never been seen before, but have some good properties. Anyway, my excitement is to understand what's making them work. Yeah, and with finite elements, of course, we go back. There were original papers by Courant, the founder of the Courant Institute in New York, by Tinkovitz and other engineers critical. I had a trip to China at that point, and there was a wonderful older scientist there who built his own computer, and he had independently the idea of finite elements. The point is that the idea really grew and developed well.
Mm-hmm. Are the Millennium Problems something you think about sometimes?
Oh, no mathematician. Well, no. I mean, of course, the great open problem for mathematicians, if we had to agree on one problem we'd like to see solved, it would be about the Riemann zeta function. But no, ordinary guy has no hope. No. My neighbors they say, well, look, there's $1 million there, Gil. Why don't you just solve the problem? Oh, out of the question.
Yeah. But was it maybe that in the break when you went to lunch or dinner that you talked to your colleagues about the Millennium Problems sometimes, or like math
problems in general? Maybe. Yeah, maybe if they're in that area. But no, we talk about math, that's for sure. But usually I'm talking to friends. So a very close friend at MIT is Alan Edelman, who's created the computer system Julia. Do you know Julia? Yeah. So he's, because he invented it, now he could make it super fast and super successful, and it's growing quickly. So that's always interesting to hear. And he's a real mathematician at the same time. So very impressive, yeah. And then I visited a group in Oxford who created a lot of math software that does extremely well.
Mm-hmm. To the audience listening to this podcast right now, there's a very beautiful video from Gilbert Strang sitting with the founder of Julia, and they interviewed you. Oh, that's a beautiful interview. I watched it yesterday before the podcast. It's really beautiful, humorous. I liked it so much. It's so cool.
Okay. Oh, yeah, that's right. Alan invited me. That of course, Julia has a Julia conference every year. And I guess I was in England and when the conference was in London. So I took the train down and talked to Alan for that interview. But I was impressed by the Julia conference. I was there on day 5, and many conferences that we've all been to. By day 5, everybody is kind of exhausted. But this conference was very active still at the end. I think people see Julia as a way to get speed with modern computing ideas, numerical and machine based.
Yeah, I agree. When you think about mathematicians, Gilbert, maybe you can give us like top 3 mathematicians that you really admire that maybe also guided you or inspired you in your life.
Okay. Well, if I pick those that guided me or inspired me, which is that narrows the field since I'm not in topology or other. So my hero as a young mathematician was Peter Lax. So he's about 95 now or more at the Courant Institute, New York University, which has been really an outstanding applied math department. And so Peter won the Abel Prize. I don't know if everybody knows that there's a prize named after from Norway, a little bit similar to the Nobel Prize, but this is a mathematician named Abel, Abel, who was an early great man. He proved that there's no explicit solution for the roots of a polynomial when the degree reaches 5. We all know the quadratic formula, and there's a similar cubic and quartic formula for degree 3 and 4 that nobody knows or uses. It would be not very stable. but it's correct. But for 5, there never will be such a formula. There never will be. That would be a waste of, you could make that $1 million problem, but nobody would ever solve it. Yeah. So anyway, Peter Lax won the Abel Prize for his career in mathematics. And so he did a lot. He also worked and met von Neumann in Los Alamos when von Neumann was doing some fluid mechanics. Anyway, Peter Lax is just a great person. A lot of us admired him very much. Mm-hmm. So I've given you one person. There are others, of course, who I admire, but I don't know their work in the same way that I would with Peter Lax.
Mm-hmm. Yeah, I think when people get asked like who are their favorite math teachers, I think in the future a lot of, or even now, people will say, well, one of them is definitely Gilbert Strang. What advice would you give students to maybe grasp such a difficult topic such as mathematics more easily? Like, how do you personally work on a hard task productively?
Yeah, well, okay. So I'm thinking the task is to learn about linear algebra. That's my life work, really, with applications to finite elements and wavelets and other and now deep learning. But the basic ideas, I've just created lecture notes for linear algebra, about 150 pages of lecture notes. So I'm thinking that could be an ebook that people would, math teachers could use it just before they go into class. They could have a quick look to see the outline of what their topic is. So I think of linear algebra as really the key steps are factoring a matrix, a general matrix. For example, eigenvalues would give a way to factor, to diagonalize a matrix. You write it, so you have this matrix and we know its eigenvalues and eigenvectors. And if we put those into separate matrices, the eigenvector matrix and the eigenvalue matrix, we can express the original matrix from those. So, but I don't know if all your audience knows about singular values. Singular values are what you do when the matrix isn't square and a matrix of data is not square. So singular value decomposition is like the eigenvalue decomposition that we all learn, but really the eigenvalues are great for symmetric matrices. And for a symmetric matrix, the wonderful fact is that the eigenvalues are all real, so it's physically good, and the eigenvectors are perpendicular, so it's just beautiful. But if the matrix isn't symmetric, all that can fail. Mm. And if the matrix is rectangular, there are no eigenvalues. So singular values are the right answer in general, and singular vectors. The main difference is when you have a rectangular matrix, then you have a basis for the rows, and the rows maybe would be in n-dimensional space, and then you have a basis for the columns, and the columns might be in m-dimensional. We have two spaces, m-dimensional space and n. Mm-hmm. So naturally, there are two kinds of eigenvectors, only we don't call them eigenvectors, call them singular vectors. So they're left singular vectors and right singular vectors. You have to have that when the matrix is rectangular. So this is a topic that most elementary math courses don't get there, singular values, but that's where the action is. If you ask a linear algebra person some problem, he or she is going to think about how to solve it using singular values.
And I think in your new book, you covered SVD, if I'm not mistaken, right?
Yes, that's right. Oh, yeah. I include it now in my course. Because if a student can learn about eigenvectors and eigenvalues, this is a small step beyond. And it's such an important step that you've got to take that step. Yeah. It's not hard. Just think of it as two kinds of eigenvectors in M and N dimensional space, because that's the shape of the matrix.
Now we talked about matrices in the beautiful interview with you and Lex Friedman. You talked about your favorite matrix. And I want to know from you is, can you maybe repeat what's your favorite matrix and also what's your least favorite matrix? Because, I mean, you can't love them all like equally, right?
No, you don't. Well, yeah, so my favorite matrix, it should be familiar. For example, you would see it in finite differences. So I'm talking about one-dimensional problems, and I'm talking about what the matrix form of second derivative. So it's the matrix that expresses second derivative in finite differences or finite elements. So, and equally spaced. So everything perfect. So remember the matrix for the second differences have a u at 1 point minus 2u at the center point plus u at the left point, right? 1 minus 2, 1, a second difference. So those numbers show up on the diagonals of the matrix. So if you look at my website, you'll see one day, to my surprise, some of the class brought in birthday cupcakes with 2's down the diagonal and minus 1's on the next diagonal. If you look really closely at the picture, you can see those on the cupcake, which the class all ate right away. Yeah,
I saw it. It was beautiful. I didn't notice first what it was, but now you explain it so everyone have an impression.
Absolutely, right. Yeah. You have to look pretty hard to see the icing or frosting that has those numbers minus 1, 2, minus 1.
Excellent. Gilbert, that was all the questions for the main podcast. Now I would go to the infamous question rampage. So I'll ask you a question, and ideally you answer them in 1 or maybe 2 sentences.
Okay.
Okay, let's start with the first one. What are you most proud of?
Most proud of? Well, I would say the video lectures and the books. Yeah, the video lectures and the books. Of course, I work hard on the research papers, and I like to look back at those, but really the books on linear algebra and finite elements and others, and the video lectures. I can imagine doing another set of video lectures based on these notes that I've completed. Anyway, that's what I think of as hopefully surviving the longest.
Yeah, I admire that from you, Gilbert, that you're not even tired. You just keep thinking about new videos, creating new content, papers, and books. I love that. Question number 2. What is the most favorite mathematical concept you ever encountered?
Oh, well, let's see. I just spoke about singular values. That's certainly a favorite, but not, I'm nobody special in that direction. So the most, it's certainly, I'll say matrix multiplication. Now your viewers will say, what? Matrix multiplication, that's just a bunch of dot products. Everybody knows that. But there's much more to it. And the new book, Linear Algebra for Everyone, it's like the new view of how to learn linear algebra. And it's based on learning matrix multiplication and factorization. So everybody knows maybe the eigenvalues and eigenvectors. We said those reconstruct the matrix. but also Graham-Schmidt, which produces orthogonal vectors, very important, very stable calculation. That's matrix factorization. And elimination, does that word elimination mean?
Yep.
The old Chinese 3,000 years ago system of subtract multiples of one row from another row. Yep. Gaussian elimination. That everybody expresses as a lower triangular matrix times an upper triangular matrix. And to see that is just pretty neat. Yeah.
That was the LU decomposition you talked about?
That's LU. That's right. That's LU. Yeah. Yeah. Okay. So I put into the book a new way to understand why do you get L times U? How does that come? It suddenly appears. You just got it right. L times U.
Beautiful. And I'll put the link to every book and also the papers that you mentioned during the podcast in the description for our audience.
Oh, thanks.
Cool. Of course. Question number 3 is a bit of a general one. One tip to make the world a better place.
Oh, I think help other people is the answer. You really, I feel we were doing pretty well. People in the world at being considerate of other people and helping them. Gosh, life isn't easy for so many people, and a little help and encouragement is really the right thing to do. Yeah, I don't know.
I love that. Yeah, that answers it completely. Next question. What advice would you give your 18-year-old self?
See. Oh, gee. Well, I have a grandson who's a good mathematician. And so my advice to him is it's a wonderful life and do it. But others in the family or friends, doing other things with their lives. I think keep learning and thinking. That's the keep interested in things. Yeah. I still like playing around after all this time. New ideas keep coming.
Beautiful. If you could have dinner with 3 people, who would it be? Could be dead or alive, by the way. Maybe a scientist you really admire, but he's not with us anymore.
And of course the other sciences. I mean, it's exciting, isn't it, how biology and understanding genetics and so forth has become in our lifetime, has become so important. And that's a world I don't know anything about, but I'm impressed by the fact that somehow scientists really successfully discovered, how things in the body work. So if I don't know who to suggest, it'd be interesting to really understand who had key ideas there. Of course, the discovery of DNA was a big one.
And then you would invite them to dinner and talk to them about life.
I certainly would. Yeah. Well, maybe not Watson. I think Crick was more. Watson is a little. I think Crick had a wider view of science, maybe. But I don't really know. Yeah.
What is a common belief about your profession that you passionately disagree with?
That mathematics is boring and too difficult. It's not too difficult. It takes practice to think in a straight line, to think, okay, if this is true and this is true, then this is true. I can remember every mathematician has to learn that process. So that's not easy. What is a proof in math? A lot of people don't worry about that, but a mathematician does have to understand the meaning of a proof and how to create one.
Got it. Topic you enjoy teaching the most? Is there a specific topic you like
Hmm.
most?
Well, I like to. I don't know if people know the book. I kind of developed the idea of the four fundamental subspaces.
Mm-hmm.
So starting with a matrix, and one subspace called its column space is all combinations of the column vectors. So you have some column vectors, maybe n column vectors, and then you take all their combinations. Now, can you understand what you get from all those combinations? It's kind of a plane, but it's a plane in high dimensions, so I can't see a picture of it really. But it's flat, whatever flat means. And these four subspaces, that was one of them, the column space, just fit together beautifully and tell you everything about the matrix. So that's sort of the idea of math. You're given a matrix, which at first it's just a bunch of numbers, m rows, n columns, m times n numbers. But then you think of it as vectors, and then you take combinations of vectors, and somehow planes and geometry appears, and you really understand the what's in that matrix. And if it's a matrix of data, you understand how to find that data, how to find the message in the matrix.
I see. Mm-hmm. Got it. What student you remember touched your heart the most?
Oh gosh. Well, my best student was, and I haven't. Other mathematicians have done much more with graduate students. I've enjoyed that, but it hasn't been sort of writing books is a different direction, and I don't. But a student that I remember happily, and he just passed away. His name was Hermann Flaschka. Oh, well, and I have another student in Germany who I have very much enjoyed, Hermann Matisse, in northern Germany. And I've had happy visits to Munich and, many places. Yeah. So, but Flaschka was just a gentle, happy spirit, and he solved a problem about nonlinear oscillations that won him a prize, and I was very happy and proud of him.
Mm-hmm. Beautiful. What is a fact about you that not a lot of people know about?
Oh, well, do you want a good fact or a bad fact?
You can give us both. I don't mind.
Well, yeah. Well, I'm proud that I was the MIT faculty tennis champion at one point in my life. That shows that the quality of MIT faculty tennis players is not so high, and that's true. But anyway, it still was a pleasure to so tennis was my game, and it's a terrific game. Yeah, so and I'm proud of the family. So personal things too, of course, very proud of seeing and interested to see grandchildren growing up and doing things.
Beautiful. I love that, Gilbert. Thanks for sharing. Assuming artificial general intelligence will be possible in 5 to 10 years, what is the first question you ask such a system?
Oh gosh. Well, I will want to know how it works.
That's good.
That's of course, like any scientist, you want to know, or engineer, you want to know, how does that thing work? Yeah. So one of my grandsons is in a little startup now, creating robots. Mm-hmm. So robotics, I should have included in my applied math course. I think it would fit. So I'd like to do that. But the idea of a little startup that makes robots and looking for some new ideas he's having a great adventure. And who knows, many startups don't find the idea that they're looking for, but I'm hoping he will.
Exciting times we live in. So 2 last questions before we wrap things up, Gilbert.
Sure.
One superpower you would like to have, what would that be?
Well, if I could learn how to do coding without making any effort, and actually how to put together machines, or how to work my cell phone or whatever. Anyway, I would be happy if it took no effort and no thought, and suddenly I was good at that. That would make me happy.
Beautiful answer. Last question of the question run page. If you were a superhero, what would your name be?
I'm not sure.
SVD man? Something like
well,
that.
SVD, that's taken. So, my new factorization is C times R. Any matrix can be written as a matrix of independent columns times a matrix of independent rows. So A equals CR. Okay, so I'll put that. And the FEM, that surely has examples. So if I do a T-shirt or something one day, I'll include FEM and A equals CR.
That's beautiful. If you need help with that, I can certainly help you to get a shirt brand.
Okay. Oh, that's fine. Okay, that would be great.
Cool.
Yeah. Well, thanks for inviting me.
Thank you so much, Gilbert. And I would like to thank you at the end from every student around the world, because you inspired millions and millions of students around the world. Whether it's like making math easier for us, providing lectures for free from MIT. I think that's a beautiful thing to do. You're a humble man. You're a very interesting person. We learned a lot about you now in this podcast. And thank you so much for coming to my rather small show. So I really much appreciate it.
Well, thank you, Joseph. It was a pleasure. Right. Good luck on all your future work. Yeah.
Thanks a lot. And we'll keep in touch, especially because of the shirts.
Okay. All right. I didn't know that. Yeah. Okay.
Take care.
Thanks.
Cool.
Good. Have a great day. Yeah.